In this module, we're talking about a type of chemical reaction called an acid-base reaction. So first, some definitions. There are several definitions of acids and bases. We'll see two of them in this topic. The Arrhenius definition of an acid is something that when you put it into water, it produces a hydrogen ion. Like hydrochloric acid, a strong acid, you put it into water, and it dissociates into the hydrogen ion and the chloride ion. Now, an Arrhenius base, when you put it into water, produces the hydroxide ion. Ammonia, you saw in the previous module how ammonia can react with water, pull a proton off of water, and make the ammonium ion and hydroxide. Well, it produces the hydroxide ion in water, so it's a base. The Bronsted-Lowry definitions of acids and bases are a little bit different. A Bronsted-Lowry acid is something that donates a proton, and a Bronsted-Lowry is something that accepts a proton. Well, if you look down here, water is donating a proton to ammonia to make ammonium, and it's lost it over here, right? So under the Bronsted-Lowry definition, water is being an acid, and that's true, it is being an acid. And you can also see that ammonia is accepting a proton from water to make ammonium, leaving behind hydroxide, and so it's accepting a proton as being a Bronsted-Lowry base. Now, when we look at a weak acid, this is acetic acid dissociating to the hydrogen ion and acetate. Another way of writing this, an entirely equivalent way of writing this reaction, is to have acetic acid reacting with water to make what's called the hydronium ion and acetate. The hydronium ion is H3O+. For us, it's going to be interchangeable with the hydrogen ion. Depends which it's more convenient to write or which explains things better. Now, if we look at acetic acid, there's 4 hydrogens in this molecule, but only one of those is what we call an acidic proton. The acidic proton is the one that will dissociate in water or will react with a base if we put a base in with it. Now, an acid can be either monoprotic, which means it has one acidic proton, like for instance hydrochloric acid. Diprotic, it has 2 acidic protons, like sulfuric acid. It could be triprotic, like phosphoric acid with 3 acidic protons. If it has more than one acidic proton, we can also call it polyprotic. So just some definitions for you. Now, so an acid-base reaction. We call the reaction of an acid with a base, surprisingly, an acid-base reaction, or sometimes a neutralization reaction. The reason for the term neutralization reaction is when an acid and a base react, what they always produce is a salt, an ionic compound, and water, which is a fairly neutral solution. Whereas before, this solution was acidic because it has an acid in it, and this was basic because it has a base in it. Now, what's a base? The bases that we will see in this course, will have, almost all of them will have hydroxide in them, and the ones that don't will have ammonia or a derivative of ammonia. So here's an acid-base reaction. Ammonia is going to be an acid. Can you predict the products of this reaction? Okay, pause it for a minute, see if you figured it out, and then, okay, so did you get the ammonium ion and the chloride ion? Or another way of writing that would be just, if we put them together, we could write ammonium chloride. Because you see what's happening is hydrochloric acid is donating a proton to ammonia, to the nitrogen in ammonia, just like we saw ammonia pull that proton away from a water molecule. Well, the acid here will donate that proton. The ammonia, the nitrogen, will accept that proton, making ammonium, leaving behind the chloride ion, or ammonium chloride. Net ionic equation for the reaction of any strong acid with a strong base. Strong base is just, it's going to be a hydroxide, a metal hydroxide that's soluble based on our solubility rules. So pretty much it's going to be, sodium hydroxide, potassium hydroxide, rubidium hydroxide, like those. But anyway, the net ionic equation is always this. That's a real handy thing to know. You don't even have to figure it out. Oh, that's a strong acid and a strong base. Boom, there's the net ionic equation. That's the chemistry. And when a strong acid reacts with a strong base, a proton reacts with hydroxide to make water. Now, acid-base titrations. Titration means you measure something, right? And when you titrate something, you're trying to almost always figure out the concentration of something in a solution. For example, this is a real common way to do a titration, acid-base titration. This is called a burette right here, and it measures how much of the solution that's in it has been added to a flask down at the bottom here. Let's say we had a solution of sodium hydroxide whose molarity we already know. And we have a solution of hydrochloric acid down here whose solution we don't know, whose concentration we don't know. What we do is we put something called an indicator. The most common one for this type of reaction is called phenolphthalein, but you don't need to really know that. But you need to know what an indicator does. What it does for you is it somehow lets you know, usually visually, when you've added the same number of moles of whatever is coming from the burette, in this case the sodium hydroxide, as you need to use up all of whatever's down here, in this case the hydrochloric acid. So however many moles of hydrochloric acid are down here, when we add that many moles of the sodium hydroxide, we'll reach what's called the end point. And what phenolphthalein does is, in an acidic solution, it's clear. In a basic solution, it's pink. And so what happens is, as you're adding the sodium hydroxide from the burette, at first you don't have enough sodium hydroxide to use up all the hydrochloric acid, so there's still some left in here and it stays clear. But as you get close to adding enough sodium hydroxide to use up all the hydrochloric acid, you start seeing little splashes of pink, but when you swirl that flask, it goes away. That means you're close to the end point. Remember, the end point is when you've added just the same number of moles of sodium hydroxide as you need to use up all the hydrochloric acid. And so what happens is you add a drop, it turns pink, then you swirl it and it goes clear. Then you add another, just a single drop or part of a drop. It turns pink and it stays pink. That's the end point. And phenolphthalein, the indicator, lets you know visually that you're right there. So we can do some acid-base titration calculations. Let's say, okay, we're titrating some hydrochloric acid with sodium hydroxide. Here's what we know. We know that the concentration of the sodium hydroxide that's up in that burette is, 0.1209 moles per liter. And we know that it took 23.22 milliliters of that sodium hydroxide to reach the end point. In other words, right when that solution first turned pink with one drop, we had added 23.22 milliliters of this solution in the burette. We also know how much of the hydrochloric acid solution was down in the flask, because we used a volumetric burette to measure it. So 10.00 milliliters. So how do we find the concentration of hydrochloric acid? Well, we need to know the balanced chemical equation. We need to know the mole-to-mole ratio between the acid and the base. In this case, it's easy because it's 1:1. But if it's not, you have to make sure you include that, and I'll show you how. First thing we do is we figure out how many moles of sodium hydroxide we added at the end point. So you just take the volume in liters. Notice I converted the milliliters to liters by dividing by 1,000. I just moved the decimal 3 to the left. Multiply times the molarity of the sodium hydroxide, moles per liter, and this gives us moles of sodium hydroxide. Or if it's not sodium hydroxide, it's whatever you know the molarity of that's in the burette. Then, now we use the stoichiometry, the mole-to-mole ratio. Take the moles of sodium hydroxide times, in this case, 1 mole of hydrochloric acid per 1 mole of sodium hydroxide. But if it's not, let's say if it's 2 sodium hydroxides per 1 mole of acid, we'd have to take that into account right here. Anyway, that gives us how many moles of, in this case, the acid there were. This is the moles of hydrochloric acid that was down in that flask in that 20 mils. So all we need to do to get the concentration of hydrochloric acid is take the moles and divide by the liters. So this many moles divided by, remember we had 20 mils, so 0.02000 liters, and that gives us our molarity, 0.1510 molar.